Hello everyone, my name is Lassi Paunonen. I'm an associate professor in mathematics at Tampere University in Finland, and this research is joint work with my former postdoc Phan. In this talk I'm going to speak about robust output regulation for parabolic distributed parameter systems. And in our main control problem, the aim is to design a control law in such a way that the measured output y of the system converges to a given reference signal asymptotically as t goes to infinity, and this convergence takes place despite the disturbance signals w. In addition, this controller is required to be robust in the sense that it will tolerate small perturbations in the form of changes and uncertainty in the parameters of the system and also in some parts of the control law itself. And as the main results, I will present a novel finite-dimensional low-order controller design method for solving the robust output regulation problem. And the main novelty and contribution of this research is that the earlier controllers for infinite-dimensional systems, which are possibly unstable, have always been infinite-dimensional systems themselves, which is very impractical from the implementation point of view. As the main novelty of the angle, we utilize the Galerkin approximation theory and model reduction in our design of the controller for robust output regulation. So throughout the talk, we will consider a linear infinite-dimensional distributed parameter system on a Hilbert space X, and we in particular assume that A generates a possibly unstable analytic semigroup on this space. And in addition, input and output operators B and C are assumed to be bounded during this talk. And in the context of such systems, our control problem can then be stated in the following way. So for a given class of disturbance signals W and reference signals Yref, we would like to find a control law such that the output of the system converges to the reference for all initial states x0, and this convergence property should be achieved even if the operators of the system undergo some small perturbations. And this control problem has been studied extensively in the literature also for infinite-dimensional systems. If the original system is already exponentially stable, or it can be stabilized by output feedback, then it is possible to design a finite-dimensional controller to solve the robust output regulation problem. This situation is studied really extensively, and for example the Reberber-Weiss paper from 2003 covers a really general class of well-posed linear systems. And typically these finite-dimensional controllers rely either on low-gain controller design or perhaps utilize the possible passivity of the systems. On the other hand, in the situation where the system is unstable, it is possible to use different kinds of observer design methods to produce an infinite-dimensional controller. Of course, from the implementation point of view, an infinite-dimensional controller is very impractical. However, there are also a few controller design methods available in the literature for unstable systems using an infinite-dimensional controller. Unfortunately, all of these methods have some severe limitations on the assumptions that need to be placed on the system, or the possibility of the so-called spillover effect, destroying the control goal. So to improve the situation, in this talk I will introduce a new controller design method for a very wide class of parabolic distributed parameter systems. In addition, the controller design algorithm is fairly simple in the sense that it only utilizes standard methods such as linear quadratic stabilization and model reduction via balanced truncation to arrive at a finite-dimensional low-order controller. So in the second part of the talk, I'll introduce our new controller design method and state our main results. We can begin by formulating our class of reference and disturbance signals more precisely. And what we assume in our control problem is that both the reference and disturbance signal are combinations of sinusoidal signals with known frequencies omega k, which can either be known beforehand or estimated alongside with the solution of the control problem, and with unknown amplitudes and phases. And what we aim to construct is a dynamic error feedback controller, which is another linear system, but now on a finite dimensional space with matrices G1, G2, and K. And this controller will produce the control input to our system based on the knowledge of its own internal state and the error between the output and the reference signal. And the controller design for robust output regulation is typically based on the internal model principle, which is really a fundamental important result characterizing all controllers which can be used in solving this problem. And in particular, a dynamic feedback controller solves this control problem precisely if two conditions are satisfied. First of all, the closed loop system consisting of the control system and the controller needs to be stable. And in addition, the controller should contain a so-called internal model of all of the frequencies omega k of the reference and disturbance signals. And in our situation, the concept of the internal model has a very concrete meaning. And this condition requires that every complex frequency, meaning plus and minus I omega k of the reference and disturbance signals, must be an eigenvalue of the main matrix G1 of the controller, and the multiplicity of each of these eigenvalues has to be at least the number of outputs of our system. And the internal model principle can be utilized very effectively in the controller design because it splits the control problem into two parts. In the first part, our aim is to just guarantee that our controller contains a suitable internal model. And in the second, our aim is then to use all the other parameters of the controller to stabilize the closed loop system. And as mentioned, the first step is typically fairly straightforward, and it is typically the main challenge to solve the stabilization of the closed loop system. And in this work, our aim is to approach this in a new way by using the Galerkin approximation theory for parabolic systems. And since the Galerkin approximations are so central to our results, I'll spend a bit of time talking about them first. And what we actually assume throughout our work is that the main operator A is associated with a bounded and coercive sesquilinear form A on a Hilbert space V, which is contained in our state space X as a subspace, and it has its own norm. And under these assumptions, we can make an additional assumption that there exists a sequence of so-called approximating subspaces Vn, each being finite dimensional, and having the property that any element phi from the space V can be approximated with arbitrary accuracy by elements in these finite dimensional subspaces and in the norm of V. And the existence of such subspaces and the approximation property with the norm on V has also been shown for large classes of convection diffusion equations and associated approximation schemes such as the finite element method and finite volume method. And with the aid of these finite dimensional subspaces Vn, we can then define the Galerkin approximation of our original distributed parameter system by projecting our system onto these finite dimensional spaces Vn. And now our aim is to use these Galerkin approximations of our system in designing a controller for robust output regulation of our original infinite dimensional PDE model. And what we obtain is a finite dimensional dynamic output feedback controller along with a design algorithm for the parameters of this system based on the frequencies of the disturbance and reference signals, the Galerkin approximation of our original system, an additional dimension parameter for the model reduction, which then determines the final dimension of our controller. Even though these controller equations may seem complicated, the bottom line is that this is simply a finite dimensional linear system which is determined by this specific block structure and the 7 matrices which are the parameters of the controller. And one particular thing to note here is that while the Galerkin approximation of the system is used in the controller design, this controller design doesn't require any information of the disturbance input operator of the system. And this is an effect of the robustness of the controller, and in particular the controller we design here will, due to robustness, work for any arbitrary disturbance input operator. And this also means that this disturbance input can be completely unknown. The design algorithm for our controller parameters can be divided into 3 steps shown here. In the first step of the algorithm, we construct the matrices G1 and G2, which are the so-called internal model of the controller. And this step is very constructive, so there are just specific formulas for these 2 matrices based on the information of the frequencies omega k and the number of outputs of our system. And in the second step, we use linear quadratic methods and solutions of Riccati equations to design an output injection gain as well as a state feedback gain for 2 finite dimensional pairs. So this is indeed a finite dimensional stabilization and detectability problem. And because of these two matrices can be designed, for example, using the built-in MATLAB routines for solving these problems. And finally, in the third step, we apply balanced truncation to a specific stable finite dimensional control system to arrive at a lower order R-dimensional stable control system. And when we have completed our algorithm, we can note that we have all the 7 parameters of our controller. So G1 and G2 come from the first step, the matrix K1n comes from the second step, and the last 4 matrices come from the third step. And the main result regarding our controller design is then stated here. We first of all assume that our control system is both exponentially stabilizable and detectable, and it doesn't have any transmission zeros at the complex frequencies of the reference and disturbance signals. And these assumptions do not lose any generality, because in fact both of these properties are also necessary for the solvability of the robust output regulation in the first place. But the main part of our result then states that if the order n of the Galerkin approximation and the model reduction parameter r are both sufficiently large, then the controller we have designed really solves the robust output regulation problem. And in particular, the controller will achieve uniform exponential convergence of the output to the reference signal for all initial states and for all reference and disturbance signals in our class. And a few comments are in order. In the second step of the controller design algorithm, where we solve these linear quadratic problems, we can set predefined stability margins for the stabilized systems, and in this way directly affect the convergence rate that our controller achieves for the output tracking. The main assumptions of the theorem that both n, the order of the Galerkin approximation, and the order r of the model reduction should be sufficiently large is definitely inconvenient from the point of view of designing controllers for actual PDE systems. And this part is definitely an important topic for future research on this subject. And it is worthwhile to note that since the approximation schemes and different types of particular PDE models can differ so much from each other, it is probable that in this research it's necessary to go to a particular class of diffusion convection equations alongside with a specific approximation scheme such as the finite element method. And finally, the required size R of the model reduction depends roughly on the rate of decay of the Hankel singular values of the Galerkin approximations. And for most classes of PDE systems, this decay is quite rapid, and this in general means that for most PDE systems it is possible to do a significant amount of model reduction and arrive at a relatively low order controller. Okay, in this final part of the talk I'll apply our controller design method for achieving temperature tracking in a rectangular room. And these simulations and the controller design were carried out by my PhD student Huhtala, and this is related to his thesis work, which is also joint work with Weiwei Hu. So we have a rectangular space with some fluid in it, and we model the temperature profile of the fluid. The walls of the room have two openings, one on the left side with an inflow of the fluid, and another one on the right side with outflow of the fluid. And our aim is to achieve output tracking of the average temperature in this red square while controlling the temperature in this blue rectangle. And in addition, there is a temperature disturbance input at the boundary at the opening of the wall, and such a disturbance input in fact fits nicely in the theoretic framework of our results in this presentation. And in this simulation example, it is assumed that the velocity of the fluid is all the time in its steady state. And in this case, the temperature can be modeled by a diffusion convection equation on the first line with the control input, and the velocity field V is determined by the incompressible steady-state Navier-Stokes equations on the second line. And finally, the temperature measurement is the average integral over the red square. And in this simulation example, our aim is to achieve output convergence to a reference signal with two sinusoidal components with frequencies 1 and 2, while at the same time rejecting the boundary disturbance with frequency 3. The reduced order controller design that Consta carried out then is based on the three frequencies 1, 2, and 3, and the knowledge that our system has a single output Y. And the PDE model is approximated with the finite element method using quadratic basis functions, arriving at a fairly high order system. And as mentioned before, the controller design can be implemented using MATLAB built-in functions, and what we end up with is a robust controller with total dimension 16, consisting of the dimension of the internal model plus the remaining parts with dimension R. And on this slide we plot the output of the system as well as a snapshot of the temperature profile, and what we can observe is nice convergence of the output to the reference signal. And in these simulations, Consta used a higher order FEM approximation for the plant to represent the situation that in our controller design we don't actually use the full knowledge of our plant, but instead it's finite-dimensional Galerkin approximation. And in fact, in this simulation, the PDE model is in fact a stable system. Because of this, we could have alternatively also used one of the existing finite-dimensional robust controllers, in particular the low-gain controller. And this controller has smaller dimension, but on the other hand, because of the low-gain design, the achievable rate of convergence is limited to roughly of order 0.1. On the other hand, our controller achieves a higher convergence rate with only quite moderate increase in the dimension of the controller. And as mentioned, in the stabilization step, it's also possible to increase this rate of convergence at the expense of increased control cost. And finally, I'll show an animation of the evolution of the control temperature profile. And the temperature profile is shown on the left here. The inlet and the place of the control input are shown at the front of the figure. The red dots inside the spatial domain denote the area where the temperature measurement is taken. And on the right hand side here, you can see the evolution of the temperature measurement as well as the tracking error. Finally, to summarize, in this presentation, I've introduced a new low-order robust controller design method for output regulation of parabolic systems. And this controller design is based on Galerkin approximations, and it is quite straightforward and easily implementable, for example, using the built-in MATLAB routines for linear quadratic design and model reduction. And here I'm also listing few of the references on which this talk is based on. The first one being our main paper on this topic, and the second one presenting extensions of the results for boundary control PDEs. And the simulation examples are taken from Konsta's paper at the MTNS conference this year. And finally, I want to also mention that the controller is also implemented in our group's software package ROARpack, which is now coming out as a MATLAB version, and it previously existed as a Python library. So thank you very much for hearing my talk.